what I want to do here is skim through this article real quick. So this article you can find in the lecture handouts for section 8.3. And my question here is, what's the main claim that this article is trying to make? And it's right here in the headline. It's saying that 53% of Americans support raising the federal minimum wage. That's 53% of all Americans that they're claiming here. And my question is, how did they get this 53%? Did they ask all Americans? Probably not. That's millions and millions of people, which is too much. They probably didn't ask everybody. I know they didn't ask me. So the question is, how did they get this 53%? And if we read or skim to the end here, it says that the poll sampled 802 American adults, which is definitely not everybody. How are they able to make a claim about all Americans from a sample of just 802 people? That's one of the main questions we'll ask and answer in this chapter. The other thing I want to point out here is the very last sentence. It says the margin of error is plus or minus 3.5 percentage points. And it also says 95% confidence level. What do those things mean? The margin of error you probably heard before on the news. In any election year, you probably heard the term margin of error. So what that means is the researchers are acknowledging that because they didn't ask everybody, they only asked 802 people, they're acknowledging that the correct answer is probably not exactly 53%. What they are saying is that it's probably 53% with an error of plus or minus 3.5%. In other words, they could be off by plus or minus 3.5%. They're saying that it could be as low as 53 minus 3.5%, which I think is 49.5%. And it could be as high as 53 plus 3.5%, which is 56.5%. So although it may not be exactly 53%, they are saying that it's somewhere in the range of 49.5% and 56.5%, which is still saying a lot, right? That's a pretty small range that you're claiming about all Americans from just a very small sample of 802 people. So this is an example of a confidence interval, which is going to be the focus of this chapter. How do we actually compute a confidence interval? Procedure for constructing a CI, so CI stands for confidence interval, for a population proportion. I'm going to go through the steps here, and then we'll talk about what they mean a little bit later. So what we're after is the population proportion. So this is the proportion of the population that have a certain characteristic. In the article, they were concerned with the proportion of the population who support raising the minimum wage. So the first step is, because we can't ask everybody in the population, the next best thing is to take a sample. So we're going to take a sample and then compute the proportion from the sample. And that's called computing the point estimate. And the symbol is p hat. P hat is the proportion you get from your sample, as opposed to the proportion you get from the population by asking everybody. Point estimate just refers to point meaning a single number. So this is just a single number that's an estimate for the population proportion that we're really after. Second step is to find a critical value. And I'm going to call it a Z star. That's based on the confidence level. Now in the article, it mentioned a 95% confidence level. And what that's referring to, it's referring to this picture, which is the same picture we've been drawing for chapter 7, the normal distribution. 95% refers to the area in the middle. And we're looking for the two Z stars that would have an area of 0.95 in the middle. So Z star is just, I'm using the star to mean It's the special z that goes with this 95% confidence level. Once you have the critical value, your next thing is to find your margin of error. In the article, this was the plus minus 3.5%. And the way you compute it is E for error, Z star, the critical value that you found in part 2, and square root p hat 1 minus p hat over n. Make sure that entire fraction is inside the square root. Once you have the margin of error, you're going to construct your interval. Which is just p hat plus or minus the margin of error. So those are steps for making a confidence interval. So let's try out these steps on an example first before we come back to the rest of this. So I'm going to skip over now to example 1. All right, this is example 1 on page 3. A newspaper polled 238 voters, and 137 of them said that they would support the funding of the new CRC library building. Part A, construct a 95% confidence interval for the proportion of voters who support the funding of the new CRC library building. So we're going to run through the 4-step process that we just talked about. The first step is to compute the p hat. So this is the proportion of our sample that would support the new CRC library building. We asked a total of 238 voters, and 137 of them said that they would support the library. So our proportion from our sample would be 137 out of the total, which is 238. On our calculator, 137 over 238. Round this to 3 decimal places, this would be 0.576. Roughly 57.6% of our sample said that they would support the new CRC library building. Step 2. Step 2 is to find our critical value, which involves drawing this picture. Okay, this is the same picture that we drew for all of chapter 7. This is the normal distribution. And it's going to be shaded in the middle for every picture in this chapter. And the area in the middle is the confidence level. So here we have a 95% confidence. So it's 0.95 area in the middle. And we're looking for these two Z stars that would have an area of 0.95 in the middle. Basically, this is a area to Z problem from our last chapter. Okay, so in our last chapter, so these were the notes from our last chapter. For an area to Z, you do Q norm. So we don't have to go to X. We're just going from area to Z here. So it's just Q norm the left area. What's the left area? Is it 0.95? No, right? So 0.95 is the area in the middle. What I want is this unshaded part on the left side. So to find the unshaded part, you're going to first do 1 minus 0.95, which I think is 0.05. And that's the unshaded part, which is the left and the right together. If I just want the left one, what do? Divided by 2. 0.05 divided by 2 is 0.025. And that's what you feed R. Okay, so Q norm in R, 0.025. And you get a Z star of, rounded to 3 decimal places here, that's negative 1.960. I expect 2 Z stars, so the negative 1.960 is the one on the left, the one on the right. Just by symmetry, it's going to be positive 1.960. Step 3. Step 3 is to compute our margin of error using this formula. So z star square root p hat 1 minus p hat over n. Okay, z star, we have two z stars. Which one do we use? I'm always going to use the positive one. So I'm going to use 1.960. Big square root. Okay, and inside the square root, it's going to be p hat, which is 0.576 from step 1. 1 minus p hat, that's 1 minus 0.576, over n, so n is the sample size, so how many people did we ask total? 238. All right, so in decimals here, I'm going to type it in exactly like that. So 1.960 square root fraction. Okay, so that just ensures that the fraction is inside the square root. And then on top here, 0.576, parentheses, 1 minus 0.576, close parentheses, on the bottom, 238. Okay, make sure what you see on decimals looks exactly like that. So in other words, that fraction, that entire fraction should be inside of the square root. And make sure that line up top is going across the entire fraction. And rounded to 3 decimal places, this is 0.063. Okay, that's the plus minus 3.5% from the article. In our case here is plus minus 6.3%. And then finally, last step is to actually construct our confidence interval, which is going to be our p hat plus or minus the margin of error that we found. So p hat was 0.576 plus minus our margin of error 0.063. And then I want to go one step further and find the low number and the high number. So 0.576 minus 0.063, that's our low number. And that's 0.513. And then our high number, 0.576 plus. And it's 0.639. And that's the final answer I want. And what this is saying is that even though we didn't ask everybody, right? We didn't ask every single voter. What we're saying here is that if we did ask every single voter, the answer is going to be somewhere between 0.513 and 0.639. All right, part B. Interpret your result in part A in a complete sentence. So this is a sentence I want you to write for all of these. Okay, we are. State your confidence level. In our case, it's 95% confidence. So we are 95% confident that, we're talking here about the proportion of voters who support the funding of the new CRC library building. So we are 95% confident that the proportion who support the funding of the new CRC library building okay, I just copied this phrase here. The proportion of voters who support the new funding of the new CRC library building is between this and this. So when we're writing a sentence, this is for the general public. So for the general public, it's better to convert these to percents. So it's between 51.3% and 63.9%. So even though we didn't ask every single voter, we're saying that if we were able to ask every single voter, we expect the percent to be somewhere between 51.3% and 63.9%. Okay, so now that we have this sentence, we can answer some questions on the next page. Part C. Based on the confidence interval, can you conclude that more than 50% of voters support the funding of the new CRC library building? So this is talking about the true population proportion that we're after. And what we know from the previous page and our sentence here is that the true population proportion is somewhere between 51.3 and 63.9%. So if we know that somewhere between 51.3 and 63.9%, can we conclude that for sure it's more than 50? Well, yes, because 51.3 is more than 50, 63.9 is more than 50, which means everything between is for sure more than 50. Right? Whatever the true answer ends up being between here is definitely more than 50. So this is for sure going to be a yes. Part D. Based on the confidence interval, can you conclude that more than 55% of voters support the funding of the new CRC library building? And all we know is that the true answer is somewhere between 51.3 and 63.9. So can you say for sure that it's going to be more than 55? No, because it could definitely be as low as 51.3%, which is not more than 55. So not all the numbers between 51.3 and 63.9 are more than 55. So this will be a no. Because it could end up being, say, 52, which is not more than 55. Part E. Based on the confidence interval, can you conclude that less than 60% of voters support the funding of the new CRC library building? Okay, all we know that it's somewhere between 51.3 and 63.9. Can we say for sure that it's less than 60? So are all these numbers in between here less than 60? No, right? Because it could be as high as 63.9, so 63.9 is definitely not less than 60. This will be a no. F. Based on the confidence interval, can you conclude that less than 65% of voters support the funding of the new CRC library building? Okay, we know that somewhere between 51.3 and 63.9, can we say for sure that it's less than 65? In other words, the question here is, are all of these numbers in between 51.3 and 63.9, are all of these numbers in between less than 65? Yeah, they are, right? So that's less than 65, that's less than 65, which means everything between is for sure less than 65 also. This would be a yes. Before we finish off the last two parts of that example, let me go back to the front page and talk about the interpretation of the confidence level. And what I mean here is, what do we mean when we say we are 95% confident? And I'm going to use 95% confidence as an example here. And what we mean by 95% confidence is that if we were to repeat this process many times, and what do I mean by this process? What I mean is taking a sample. So here we're taking a sample of 238 voters. So if I take another sample of 238 voters, then the number who support the new library building will probably change. So this 137 will probably change, which means the p-hat will probably change, the margin of error will change, and the confidence interval that we end up with will change. So if this process is repeated many times, and what I mean by this process is taking a sample and constructing the interval, the 95% is saying that we're going to catch the true population proportion inside that interval 95% of the time. So in other words, this 95% is the success rate of this process producing an interval that will have the true population proportion in it. And that's what this picture is trying to illustrate. The line here is the true population proportion that we're trying to catch. And these are intervals, these repeated intervals. And I think there's 20 of them total. And notice that most of them catch this true population proportion in the interval, which also means that 5% of the time, you're going to get an interval that misses. And this is represented by this interval here that misses, that doesn't have this true population proportion in it. All right, so we know how to find a confidence interval using those 4 steps. What I want to do here is talk about why that works. So our goal is to catch the true population proportion from a population that I know nothing about. So the population could have some wild distribution. But from chapter 7, I don't really care. Right? From chapter 7, the central limit theorem says, as long as I pick a sample size big enough, the picture is going to look like this. And moreover, the mean is going to be the same as the original population. So instead of trying to catch this p from the original population, I'm going to try to catch this p, which is the same. Okay. Now, where does the 95% come in? The 95% refers to the area in the middle. And in chapter 7, right, we talked about an area to x problem, right? So I gave you 0.95 in the middle, and you found these 2 x's. Now here, I don't really care about those 2 x's. What I care about is how long is it from the middle to the edge here, right? That's actually the margin of error that we're finding. So in chapter 7, right, to find the x's, we did x, the mu, or sorry, we did the mean, which is the middle, plus z times the standard deviation. So we start with the middle, and the z times standard deviation, that just tells us how much to go up by to get to that edge. So here, since I'm not looking for the edge, I just need to know how far to go up. You're just finding the z times the standard deviation, which is exactly the formula for margin of error, right? Z times this big square root. But this big square root is just the standard deviation for the proportion situation. So what we're actually doing is for the margin of error, we're finding the distance from the middle to the edge. And what we know from chapter 7 is that given this picture, if I take a sample and find a proportion from the sample, in other words, find a p hat, I'm not going to always hit p exactly, right? This p hat is not going to be equal to p, right? That's hard. That's like hitting a bullseye. But I do know that 95% of the time, I am going to end up in this shaded area somewhere. Okay, so say I end up right here. That's good because if I end up in the shaded area and I go up and down using the margin of error, then I will catch the true population proportion. And this picture says that that's going to happen 95% of the time. 95% of the time, when I take a sample and look at p hat, I'm going to end up in the shaded area. And if I end up in the shaded area, when I go up and down by the margin of error, I'm going to end up with an interval that catches the true population proportion. And that's why it works. There's 2 things that affect how big or how small the margin of error is. So here's example 1. We got a margin of error of 0.063. Okay, so there's 2 things that are going to affect how big or how small that margin of error is, which in turn affects how wide or how narrow the interval we get is going to be. And those 2 things are, the first thing is the sample size. Okay, what happens when we use a bigger sample size? If we go back to our formula for finding the margin of error, okay, we're dividing by the sample size. So we're dividing by n here. So if we're dividing by a larger sample size, so if you're dividing by a bigger number, then overall you can get a smaller number. Okay, so if we divide by a larger sample size, we're going to get a smaller margin of error or a narrower interval. Okay, which means if we do the opposite, a smaller sample size, you'll get a wider interval. The other thing that affects how big or how small the margin of error is your confidence level. Okay. A larger confidence level has to do with this picture. A larger confidence level means that this shaded area is larger. So if you have a larger shaded area, then these two z stars would have to be wider, right? In other words, they'll be bigger, and you're multiplying by a bigger number, which means your margin of error would be bigger. For confidence level, a larger confidence level will end up being a wider interval. Which means the opposite, a smaller confidence level, will result in a narrower. Or a smaller margin of error. So now we're ready to answer those two questions at the end of example 1. Back to example 1, part G. If the sample size were 300 rather than 238, would the width of the interval be wider or narrower than the result in part A? So originally we used 238 as the sample size. If we change that to 300, what would happen to the width of the interval? So if we change that to 300, right, you're dividing by a bigger number. So because you're dividing by a bigger number, overall, you'll get a smaller number for the margin of error, which will give you a narrower interval. So this will be narrower. Right, if you need to, go back to the notes that we just talked about. 300 will be a larger sample size, so larger sample size will be a narrower interval. Part H. If the confidence level were 98% rather than 95%, would the margin of error be larger or smaller than the result in part A? Confidence level refers to this picture. Originally, it was 0.95. If we change that to 0.98, right? If we made the shaded area bigger, then these stars would have to go out, which means it'll be bigger, it'll be wider. And wider would mean a larger margin of error. And then once again, if you need to, go back to the notes that we just talked about. Right, 98% would be a larger confidence level, which would result in a wider interval or a larger margin of error. Example 2. A survey is to be conducted in which a random sample of residents in Sacramento would be asked whether they favor or oppose making the 2 years of community college free. How many residents should be polled to be sure that a 90% confidence interval for the proportion who favor free community college will have a margin of error of 0.05? Now, this example differs from example 1 that we just did. In example 1, we had the sample already, right? We collected the data already and we're constructing the confidence interval. This example, example 2, is even before that. So even before that, in planning the study, I want a confidence level of 90%, and I want to shoot for a margin of error of 0.05. And the question is, how many people should I ask? How many people should be in my sample? And to answer that, I have to go back and talk about determining the necessary sample size. How do we decide how many people to ask? So I'm going to start off with our formula for margin of error. And what I want is the sample size. So what I'm going to do here is do some algebra. So you don't have to write this down, just follow along. If I want the n by itself, first thing I'm going to do is I'm going to divide both sides by z star to get this z star to the other side. So the right side would now be just this big square root. Next thing I need to do is get rid of this square root. So to get rid of this square root, I'm going to square both sides. So when I square both sides, I'm going to get e over z star squared on the left side. On the right side, when I square it, that square root is going to go away. And I'll end up with p hat, 1 minus p hat over n. I'm going to multiply the n over to the left side. And then finally, to get the n by itself, I'm going to divide both sides by this thing, which is the same thing as multiplying by the reciprocal. So I'll end up finally with this. So when I flip that, that's going to be z star over e squared. And that's the formula that we'll need for finding our sample size. Now, z star, that has to do with our confidence level, right? So whatever confidence level we choose, that gets us our z star to plug in here. E is the margin of error that we're going to shoot for. And the question is, what do we plug in for p hat? So p hat, remember, is the proportion that comes from our sample. But what we're talking about here is even before we even have any data, right? So we're deciding how many people to choose, so we don't even have a sample yet. So what do we enter here for p hat? And the answer is if there's a prior estimate for p hat, use it. So if there's another study that someone else did that has a prior estimate for p hat already, you're going to use it. If no prior estimate exists, you're going to use the next best thing. So we're going to use a p hat of 50%, which is 0.50. And this number comes from, for my calculus students here who know calculus, 0.50 is a number to put in for p hat that will give us our biggest n. Right? So the idea here is that if you don't know anything about p hat, then you're going to use 0.50 and use the biggest sample size, because the biggest sample size is going to be the safest for us. Back to example 2. We're looking for a sample size, so we're going to be using the formula that we just talked about. Let me recopy that. Okay, so let's first talk about the z star. So z star has to do with the confidence level, and it has to do with this picture. Okay, and the shaded area in the middle is the confidence level that we're talking about. So here we're talking about what confidence level? 90% confidence. So the area in the middle here is 0.90. And we're looking for these two z stars that have 0.90 in the middle. This is an area to z problem, which means we'll be doing Q norm. And Q norm, you've always feed the left area of your picture. So I'm looking for this left unshaded part. So to find this left unshaded part, I'm going to first do 1 minus 0.90. Okay, that should give me the unshaded part. 0.1. But that unshaded part includes the left and the right together. I just want the left, so to get just the left, divide that by 2. So 0.1 divided by 2. 0.05. That's the unshaded left part that I want, and I'm going to feed that into R, so 0.05. Okay. In R Q norm, and round this to 3 decimal places, this gives me my z star negative 1.645. Okay, from my picture, I expect two z-stars, right? The negative is the one on the left. The one on the right should be positive, 1.645. Okay, so that gets us our z-star. E is our margin of error that we're shooting for, which is this 0.05. And then the question is, what do I put in for p hat? So p hat, remember, we're talking about the proportion who favor free community college. So if you have a product estimate for that proportion, use it. If not, we're going to use 0.50. Okay, so part A says a previous study suggests that the proportion who favor free community college is 84%. So we do have a product estimate for p hat here, which is 84%. So we'll use it. So we're going to use 0.84 for the p hat. One minus 0.84. Z star we said was negative 1.645 or 1.645. I'm going to use the positive one. So 1.645 over E, the margin of error we said was 0.05. And then don't forget this square. And then now enter this into decimals. (0.84) parentheses 1 minus 0.84 parentheses fraction 1.645 on top, on the bottom 0.05, close parentheses, and then square it, so don't forget the square. So I got 145.476. Now, we're talking about sample size here. In other words, how many people should we ask? So we can't ask 0.476 people. So how many people should we ask? So in other words, how should you round this? Should we round this to 145? So remember, this sample size is going to get us exactly a margin of error of 0.05. If I rounded this the normal way to 145, that would mean a smaller sample size, right? We're going down to 145. If we use a smaller sample size, we'll end up with a wider interval or a larger margin of error. So if I round this down to 145, that's going to get a margin of error that's bigger than 0.05, which I don't want. So you're always going to round up. Okay? So this gets bumped up to 146. So let me write that down. Okay, we're also going to round it up. So we should ask 146 people. Part B, estimate the sample size needed if no estimate of P is available. So we don't have an estimate for P. We're just going to use 0.50 for P hat instead of 0.84. So we're just going to do exactly the same thing, except instead of 0.84, we're going to use 0.50 for the P hat. Z star should stay the same because we're still talking about 90% confidence, so it'll be the same picture, which means you'll get the same Z. And then we're still talking about a margin of error of 0.05. Okay, let's enter this into Desmos. 0.50 and minus 0.50 fraction 1.645. On the bottom, 0.05. Close parentheses, square it. 270.603. Okay, but once again, we're always going to round that up. So this gets rounded up to 271 people. So we don't know anything about the proportion, then we have to ask a little bit more people. So 271 people as opposed to 246 people. Part C. If the survey wanted to estimate the proportion of the entire state of California rather than just Sacramento, who favor free community college, would this necessary sample size be larger, smaller, or the same? Okay, so this question started off by asking finding the proportion of people in Sacramento, and we had to pick 146 people and 271 people. Now, if we want to know about the entire state of California, would you ask more people, less people, or the same amount? So you would think that because California is so much bigger than just Sacramento, you would need more people. But it turns out that if you look at, right, so if I go back and redo this problem and replace the word Sacramento with California, what actually changes? Does the p hat change? No. Does the z star change? No. Right? It should still be the same picture, which means the same z star. Would the margin of error change? No, we still want a margin of error of 0.05. So even if I change the Sacramento to California, nothing changes in the calculation, which means you should be using the same sample size. So it should be the same. It's always going to be the same. So that's kind of counterintuitive, right? So even if I replace California with the entire nation or even the entire world, you still would only need 271 people, which is pretty cool. So what I want to say down here is the row of population size. So the population size has no row. Has no row or no effect on the sample size required. So whether we're talking about just Sacramento, state of California, the entire nation, the United States, or the entire world, if you want a 90% confidence interval with a margin of error of 0.05, and you knew nothing about the proportion, you would still only need 271, which is pretty incredible. Example 3. Joe and Sally are going to construct confidence intervals from the same simple random sample. Joe's confidence interval will have level 90%, and Sally's will have level 95%. Which confidence interval will have the larger margin of error, or will they both be the same? What factors affect how big or how small the margin of error is? And it's sample size and confidence level. Now, it says that they're using the same simple random sample. In other words, they're using the same sample size. So sample size is not going to be the one that affects who has the larger margin of error. What will affect who has the larger margin of error is whether one of them is using a 90% level, confidence level, and the other is using a 95% confidence level. And confidence level refers to this picture. And we're talking about the area in the middle. So which one is going to get a larger margin of error? 0.90 in the middle or 0.95 in the middle? It's going to be 0.95, right? So 0.95 will be a larger area. A larger area means that these z stars will have to be wider, and a wider interval means a larger margin of error. So 0.95. So the 95% one is going to have a larger margin of error, which is Sally's. Right, if you need to, go back to the notes here. Right, I want a larger margin of error, which means the same thing as a wider interval. A wider interval means you're looking for a larger confidence level, which would be the 95%. Part B, which confidence interval is more likely to cover the population proportion, or are they both equally likely to do so? So what I mean by cover here is which one is more likely to catch the true population proportion. And remember, when we talked about the interpretation of the confidence level, right, that these 90% and this 95% are the success rate of catching the true population proportion. So it is how likely you are to catch the true population proportion. So which one is more likely to happen, 90% or 95%? 95%, right, the bigger one. But this is also 95%, which is also Sally's. All right, have a good one. Talk to you guys later.